Good afternoon, class. Can you hear me okay? Okay. Thank
Yes,
you.
sir.
Thank you. Okay, before I start, any questions with regard to the subject matter from the last meetings? Okay, kung wala, I'll show what I prepared for this afternoon. Before doing that, I just wanted to announce that I'm not going to be able to meet you this coming Thursday. No, I have an important activity that I have to attend face to face. So I will not be able to conduct a synchronous session this Thursday. Hindi ko mako-cover yung last topic for module 2, which is operational amplifiers. So please just go through the material and go through the video recording, and if you have any questions, you can email me directly or you can post your questions Piazza. And if I appreciate it if you also tell your classmates that you know that are not here right now who are planning to attend, appreciate it if you also tell them. Although I will make an announcement too by email. Okay, so today I'm going to discuss MOS transistors, metal oxide semiconductor transistors. I took out the video recording for this module because, to be honest with you, as I was going through the slides, I discovered some errors. And I already corrected the slides. If you downloaded the slides from Uble, please download the latest version, which I corrected. So I already corrected the slides, but because my video recording used the old slides, I didn't want there to be errors in the slides. So I'm going to redo that recording. So if you're wondering why it was taken down, that's the reason why I took it down. Okay, anyway, I'm going to present a subset of those slides now, just to make things clear for you. Okay, so this is our third session. In my slides and in my video lecture, I went through a very simplified process of how a MOS transistor is fabricated. I'm not going to do that now. I'll just let you review the video recording when it is back online. Let's start with the simplified structure of your MOS transistor. So this is the simplified structure of your MOS transistor. This is the cross section. So cross section ito. Okay. So you have a gate. You have three terminals. You have four terminals. You have a gate. You have your drain. You have your source, and then you have a bulk terminal. You also have a substrate. Okay, and it just so happens that the substrate and the bulk are the same area. The bulk and the substrate are the same area. Okay, I added this in the modified slides that I created. Okay, the reason why you call it a MOS transistor is because this layer, which is polysilicon, used to be metal. This used to consist of metal. Then here you have an oxide layer. Oxide, this is silicon dioxide, which is actually an insulator. And then here you have semiconductor material. So if you take a look at these three layers, so you have what used to be metal, then oxide, then semiconductor. So that's where MOS came from. Okay. Notice that this is actually a capacitor. If you take a look at the structure of this, from the gate to the substrate, you actually have a capacitor where your dielectric is the oxide. So gate to substrate is a capacitor. This is a capacitor with your oxide as your dielectric. Okay, this is the simplified structure of a Pmos transistor. So I did not show this in the original slides. I added this. Usually, we fabricate both NMOS and PMOS transistors in the same substrate. No? So NMOS at saka PMOS usually fabricated on the same substrate. The only exception is when you are buying a discrete Pmos transistor. Okay, so how do you fabricate the Pmos transistor? Well, so in the substrate, you fabricate your bulk. So this is your bulk. So how do you do that? Your substrate originally has acceptor impurities. So you diffuse donor impurities, and the number of donor impurities should be able to overcome the number of acceptor impurities so that your material will now become net N-type. And then in this bulk, what we call the bulk, we diffuse again acceptor impurities. So the number of acceptor impurities will again overcome the donor impurities. So you get again P-type here. So this substrate, you will get an N, and then you will get a P again, and then you fabricate your gate and your your silicon dioxide and your gate. Your terminals are the same. This is the gate, this is the drain, this is the source. In the NMOS transistor, your substrate is usually connected to your bulk. So the B terminal and the substrate are the same terminal. But in the PMOS transistor, B and substrate are different terminals. So your bulk and the substrate are different. Unlike here, the bulk and the substrate are the same. Okay, so that's one major difference between the PMOS and the NMOS. Let's go to the theory of operation. Okay, normally we connect the bulk and the substrate and the source rather together. No? So by the way, the S is called the source. No? So normally we connect the bulk and the source together. So normally that is shorted. And normally we connect the substrate to ground. So typically the substrate is connected to ground. So effectively, the source is also now connected to ground, no? Because the source is connected to the bulk, but the bulk and the substrate are the same thing. They're the same area. So the bulk is also typically now connected to a ground. You just consider this to be like a conductor. Okay, what will happen if I apply a voltage VDS where my drain is positive with respect to my source? Okay, I don't expect any current to flow. Can somebody explain to me why current will not flow? Okay. Can somebody explain to me why a current will not flow? Actually, nababasa nyo rito eh. Anyone?
Is it because the depletion region between the N and P, the junction?
Well, you have an idea, no? You have an idea, but okay, maybe to illustrate it better. Okay, what do I have here? I have an N to P. No, I have an N to P. So effectively, this is a diode. This is a diode in this direction. Okay. Here I have a P to N, and so I have a diode in this direction. And then you can consider this to be like a conductor. So what do we have?
So they're reverse biased.
Oh, so nakikita mo na, no? One of the diodes will be reverse biased, though. This diode will be reverse biased. And therefore, if there's current that's going to flow here, ang magflow will be approximately equal to 0. Because, well, you will have a very, very small current that you're reverse saturation current. No? But for all practical purposes, that's approximately equal to 0. Okay. So a voltage between the drain and source will not result in current flow. So even if we apply this voltage, you're not going to get current flow because of the reverse bias drain to substrate junction. No? This junction, this drain to substrate junction is reverse biased, and therefore current will not flow. Okay. By the way, I mentioned this earlier, B is connected to ground. My bulk is connected to ground through this path. Okay, meaning to say that, okay, between this from this N plus to the bulk, okay, I'm reverse biased. No? So this is, remember, this is connected to the positive terminal. Tignan nyo tong VTS, ano? This is connected to the positive terminal. And then my bulk is connected to my ground. So this is reverse biased. Okay. This is going to be unbiased. No, the voltage between my P and my N plus is going to be 0 because they're shorted. It's going to be unbiased. In both cases, magkakaroon ako ng depletion region. So there's going to be a depletion region here. There's also going to be a depletion region here. Yeah, I'll just ask, no? Where will the depletion region be bigger? Will it be here on the right or here on the left? Can somebody shout out an answer? Right or left? I'm just exercising your what you learned about PN junctions and depletion region. Anyone?
Is it in the right, sir? Because it's like reverse bias. Directly.
That's right. Yeah, it's on the right. No? It's going to be more heavily. It's going to be more heavily reverse biased here, because of this positive terminal. No, you have a voltage VDS here with respect to this, so this is going to be more heavily. This is going to be heavily reverse biased, whereas this, it's just unbiased. There's no bias voltage here because it's shorted together. So the depletion region here is going to be bigger than the depletion region here. Okay. The important thing is, yeah, they both have depletion region around it. Okay. So how does the MOS operate? Just a while now. Right. Okay. So how does the MOS operate? Okay, let's forget the drain to source. Let's apply a voltage between gate to source, where my gate is positive with respect to my source. So I apply this voltage VGS. So this is a capacitor. Okay, this is a capacitor. What will happen is this capacitor will have the top plate positively charged with respect to the bottom plate. No? I don't know how much about capacitors you've learned, but there's going to be a displacement charge. Displaced charges here. This is going to be positive with respect to this. In other words, there's going to be an electric field that will form across the oxide layer. So this oxide layer, there's going to be an electric field that will form there. Okay, what will that electric field do? That electric field will cause electrons in the substrate to be attracted to this area. Okay, you might think of it intuitively as something like this, no? Since this is positively charged, that acts as a magnet for electrons here. Okay. Now, are there electrons in the P substrate? Remember, this is a P-type. Yes, there are electrons in the P substrate. These are intrinsic electrons. These are electrons due to electron hole pairs created because of the temperature not being at 0 degrees Kelvin. So thermally generated electron hole pairs are going to have intrinsic electrons, and those electrons are going to be attracted to this particular region. so that at steady state, this becomes n-type. When a lot of electrons, of course, that depends on the value of VGS, no? But when a lot of electrons are now in this area, that area becomes n-type, and you can no longer distinguish where the source and drain is as opposed to this region. Okay. We call this an inversion layer. Inversion layer. We also call it a channel. So when this is large enough, when VGS is large enough, we get an inversion layer here, okay, so that this becomes a contiguous n-type from D to S. And we define the threshold voltage VTH, that is the value of VGS, where your carrier concentration here of electrons is equal to the carrier concentration here of holes. So you have a carrier concentration here. Now you have a small letter n, number of electrons per cubic centimeter. The value of n here becomes the same as the value of small letter p here at VGS equal to your threshold voltage VTH. Okay. So what will happen now if I apply now my VDS? Okay, so from here, I apply this VGS, assuming VGS is greater than equal to my VTH. I'm going to have a channel here, or yeah, a channel here. If I apply now my VDS, what will VDS see? What VDS will see now is a resistor. Because now, I have a value of conductivity from my drain to my source. Magkakaroon ako ng conductivity rito. And therefore, when I apply my voltage VDS, my drain to source voltage, what this will see is a resistor and current will flow. Okay. Current will be due to the flow of electrons. So current is due to the flow of minority chargers in your substrate. Current is due to the flow of electrons. My electrons are flowing. Where are my electrons flowing? Is it from left to right or right to left? Iba naman ang sumagot, no? Can somebody just shout out the answer? Will my electrons flow left to right or right to left?
Left to right.
Right to left. Think about it some more. We're talking
Left to
about
right.
electrons. So yeah, of course, no. If it's not right to left, it's left to right, no. My electrons will be flowing from left to right. My electrons will be attracted to the positive terminal of VDS, and then my current is opposite the direction of the flow of electrons. That's why my current is right to left. Okay. So this is why you call this the source, because this is the source of charge carriers. And you call this the drain because this is where the charge carriers end up going. No? So that's the reason why this is called the source. The source is the source of charge carriers. So the electrons come from the source, they move toward the right and are collected by the drain. So there's some parallel with emitter and collector in your BJT. Your BJT, the emitter is the source of your charge carriers, and then your collector collects the carriers. So dito, source at saka drain ang tinatawag. Okay, the important thing here is this, no? VGS can be used to modulate the flow of current. Okay. Intuitively, the larger the VGS, the more charge carriers here. Kasi kung malaki to, that means your electric field across your oxide layer is larger, and therefore you will attract more electrons in this area. And if you attract more charge carriers, you have a lower resistivity or a higher conductivity. And if you have a higher conductivity, then the value of your current will become larger. So what I'm saying is you can actually control the flow of current using this VGS. Okay, so VGS can be used to modulate the flow of current. You call this an enhancement mode MOSFET. The reason why it's called an enhancement mode MOSFET is initially there was no channel. Sorry, no. So initially there's no channel. Okay. And then when you apply your VGS, you enhance a channel. The VGS enhances a channel. And so you call it an enhancement mode MOSFET. Okay, two more things that I want to show here. Your depletion region now exists here, no, all throughout this area. Because now, all throughout this area, I will either have a high reverse bias between my N and my P. So we're talking here about my N region. This is my N region, the channel or my drain and source, and my P. Here I will have a high reverse bias. Here I will have it unbiased. And then as I travel from the right to the left, okay, the amount of reverse bias between the N and the P decreases, no? Kasi dito, ang reverse bias ko is BDS, no? Remember, my P here is connected to my bulk, right? And therefore, the reverse bias here, is BDS. Here, the reverse bias here is 0. As I travel from right to left, the amount of reverse bias linearly decreases, right? Because imagine this is a resistor. So as I travel from right to left, okay, the voltage drop across the resistor will be smaller until here the voltage drop is 0. And that's the reason why your channel will also have a shape. Okay, because the value of VDS, the value of VDS, well, not VDS, no, the value of reverse bias will decrease the electric field here. Okay, the value of reverse bias will decrease the electric field here. So here the reverse bias is very high. Okay, here the reverse bias is low. And then you have a linear decrease, more or less linear decrease in the electric field across your oxide layer. So your channel is going to have this type of shape. So I just wanted to show that here, that VDS changes the shape of the channel. Okay. Are there any questions with regard to that? Any questions? Okay, so for the Pmos transistor, it's going to be very, very similar, but this time all of the voltages would be reversed, and then the current directions will be opposite that of the NMOS. So if here we applied VDS, now I'm going to apply VSD. In other words, my S is positive with respect to my D. And if here the direction of current is inward, here it's going to be outward. Okay. My VSG is going to be my source to gate voltage. Okay. The polarity has to be source positive with respect to my gate. Okay. Source positive with respect to my gate. Okay. So that this area will attract holes. No? So the channel that will be enhanced in this particular area is going to be a P channel. So to create a P channel here, you have to attract holes from your N bulk. No? We call this area the bulk area. You have to attract holes from the N bulk. So the same principle. These holes are thermally generated intrinsic holes. They are intrinsic holes. They are attracted to the area underneath the oxide because of the negative terminal of your gate with respect to your bulk, with respect to the bulk. So the bulk is negative with respect to the gate, and therefore you attract holes here. The value of your threshold voltage, the value of your threshold voltage will actually be negative. But because we are referencing the source to be positive with respect to the gate, then we just say VSG will be greater than the absolute value of your threshold voltage. Because if it's VGS, no, then we're going to say VGS should be less than or equal to should be greater than or equal to VTH. No, it's actually if you go by what we did here, the same thing we did here, we are saying that VGS should be greater than or equal to VTH. No, but this VTH is negative. The threshold voltage is negative. So we just say, so that we always deal with positive values, because this will also be negative, no? VGS will also be negative. We just say VSG should be greater or equal to the absolute value of VTH, so that it's not so confusing. Okay. Now notice that current will be due to the flow of holes. Where will your what direction will your holes flow? Your holes will flow from the source toward the drain. So source to drain pa rin, no? Dito nang gagaling yung holes, dito siya aabot sa drain, and that constitutes now your current in the counterclockwise direction. Your current direction is the same direction as your direction of hole flow. Okay, notice that from P to N, it will still be reverse biased, because this is negative. No, this is negative. So this is negative connected to the P, my positive connected to my N. So this is still reverse biased. This is still unbiased because my bulk and my source are connected. So I still get my depletion region here. Okay. Meron pa rin akong depletion region rito. On the other hand, from my bulk to my substrate, okay, notice that my bulk, okay, my bulk is connected always to the positive, right? Kita nyo rito, the bulk is connected to my positive, right? My substrate is usually connected to ground, and therefore from my bulk to the substrate, this is the N is positive, the P is negative. This is also reverse biased. So magkakaroon din ako ng depletion region dito. Okay, what does this depletion region do? This depletion region will isolate this transistor from other transistors in the circuit. No? Because in my substrate, I can have a large substrate. I can have many transistors fabricated on the same substrate. That is the principle of an integrated circuit. In an integrated circuit, you have one substrate, and then you have many transistors that are fabricated. Because there is this depletion region here, okay, that is now isolated. Okay, your substrate is now isolated, or rather, your transistor is now isolated from other transistors. So it will be isolated from this transistor. So I can have this transistor coexisting with this transistor, and the two of them will not be connected to each other, unless, of course, I connect the two together. Are there any questions? So those were the little tweaks I made to the slides from the original slides. Okay, notice the same thing. This is going to have a shape. Okay, that's going to have a shape. And the reason for that is this P plus to the bulk here will be larger because of this VSD than the P plus to the bulk here, which is smaller because these two are shorted together. Okay, so these are enhancement mode MOSFETs. Here I am enhancing an N channel. Here I am enhancing a P channel. Meron din tayong tinatawag na depletion mode, depletion type MOSFETs. I'm going to just introduce this just for completeness. Actually, the analysis of enhancement and depletion type MOSFETs are very similar. What is the difference between the two? The difference between the two is in depletion type MOSFETs, there's already a channel that is prefabricated. So in the fabrication process, for example, this is an N type or an NMOS depletion type MOSFET. Okay, in the fabrication process, naglalagay na sila ng channel dito. Dito naman, yung P-type, naglalagay na sila ng channel dito during the fabrication process. So even if there's no gate to source voltage, if I apply a voltage between my drain and my source, a current will flow kasi meron ng resistivity, meron ng conductivity to. There's already a conductivity here. So if I apply a voltage this way, kahit na wala akong gate voltage, expect a current to flow. I will not be equal to 0. So if that's the case, ano yung silbi ng gate? What is the function of the gate in this particular case? The function of the gate is to deplete the charges here. Now, how do you deplete the charges there? You repel them, no? You push them away. Okay, you push the charges here away by applying, okay, a negative voltage at the gate with respect to the source. So if I apply a negative voltage at the gate with respect to the source, so that will look something like this. Negative voltage at the gate with respect to the source. The electrons here will be attracted toward the positive terminal. No? So the electrons here will be attracted this way. Will be attracted away from this area. So if this voltage is large enough, then this area becomes depleted of charge carriers. And when that happens, current will stop flowing. Current will stop flowing. So the difference between an enhancement type and a depletion type, in an enhancement type, you apply a voltage to create a channel. In a depletion type, you apply a voltage to destroy the channel or to remove the channel. And you remove the channel by repelling away the charge carriers that are existing underneath the oxide layer. You repel them away by applying the appropriate polarity of voltage. So the two can be analyzed exactly the same way. The way you can think about it is in the depletion type MOSFET, your threshold voltage is actually less than 0. It's a negative value. As long as you're below that negative value, there won't be any charges here. But as soon as you go above that negative value, then you start to have charges here. So the only difference is your threshold voltage for NMOS is less than 0. And for PMOS, your threshold voltage will now be greater than 0. Of course, this is reference to VGS, reference to the gate being positive with respect to the source. Okay. So these are the circuit symbols for your NMOS and your PMOS. We show 4 terminals, the drain, the gate, the source, and the bulk. Okay. Sometimes we just show it this way, the gate, the drain, and the source. And we can show it this way when my bulk is connected. When my bulk is connected to my source. So if my bulk is connected to my source this way, then we can show it this way. Same thing here. When my bulk is connected to my source this way, then I can show it this way. Usually, integrated circuits, usually your bulk is always connected to your source. And that's why usually these are just the symbols that we use. So here, no? The bulk connected to the source. Okay. And here, the bulk also connected to the source, except that here, the bulk is grounded. Here, the bulk is at a positive supply with respect to the source. Okay, what are the VI characteristic curves? How do the VI characteristic curves look like? Okay. So let's assume that VGS is fixed. So assume that the value of this is fixed. Hindi natin gagalawin yan. Of course, there has to be a channel. There has to be a channel here. Okay. So for there to be a channel here, we know that VGS has to be greater than or equal to the threshold voltage. So what we will do is we will apply VDS and we will vary the value of VDS. So let's start with VDS being equal to 0 and let's slowly increase VDS. So we know that when VDS is equal to 0, of course, no current will flow, and your channel is not going to be inclined, no? Your channel is going to be straight. Ang magiging korte nito, diretso lang. Okay, as you increase VDS, what is this? This looks like a resistor to VDS. The channel looks like a resistor to VDS. So as you increase VDS, expect the current IDS to start flowing. And because it looks like a resistor, initially, that is going to look like almost a straight line. No? This is not exactly straight. There's a little bit of curve here, but it will look almost like a straight line. And you call that the linear mode of operation, where VDS increases, where IDS increases with VDS. IDS and ID are the same. So itong IDS, that's the current from drain to source. That's equal to ID. So I already mentioned that this is going to have a slope. And the reason for that slope is here, the N to P reverse bias is going to be greater than here. No? Or along the oxide layer, okay, you have a smaller electric field here than here. The electric field here decreases because of VDS. So originally we had a VGS applied. Well, you have VGS applied uniformly here, no? So you have VGS here, but here, no, you have VDS, no? Here in the bottom you have VDS. So the voltage across your oxide layer is actually VDS minus VGS rather minus VDS. So as VDS increases, this is going to become smaller because the voltage across your oxide layer is VGS minus the VDS here. You can think of it like node voltages, no? Node voltages. What is your node voltage here? Your node voltage here is VGS. What is my node voltage here? My node voltage here is VDS, right? Because this is connected to VDS, which is connected to my ground. So if I take a look at the voltage across the oxide layer, V oxide, that is just VGS, the node voltage here, minus the node voltage here, minus VDS. No, and here on the right, that's greater than here on the left. Again, that's why you have this slope. What will happen if I make this larger? No? Let's say I continue to make that larger. At some point, okay, the voltage across my oxide layer will become 0. Remember that, yeah, the voltage across my oxide layer is VGS minus VDS. Okay. At some point, will not be, no, not 0, no. At some point, the voltage across my oxide layer will become less than VTH. Will become less than VTH. Okay? Dahil lumalaki yung VDS, so paliit ng paliit ito, at some point that will become less than your threshold voltage. And when that happens, your channel will disappear. So here, I show you that the channel actually disappears. When does it disappear? When VDS becomes greater than or equal to VGS minus VTH. Okay. And that's easy to see, no? From this equation, this has to be greater than VTH, no? So dapat VGS minus VDS should be greater than or equal to VTH. Okay. So when VDS okay, this is for your channel to exist, no? For your channel to exist. So your channel disappears when, okay, your channel disappears when VGS minus VDS is less than VTH. Okay, so that means that VDS is now greater than VGS minus VTH. Yun ang sinasabi ko dito. The channel becomes pinched off. Okay, what happens when the channel becomes pinched off? Ang mangyayari, well, first of all, I sub D will not be equal to 0. No? It will not be equal to 0. This is where a lot of students get confused. You have a depletion region here. You have a depletion region here. And in a depletion region, there are no charge carriers. And students have this idea that as long as it is a depletion region, then current cannot flow. Well, if that's the case, then how come current can flow through a diode when a diode has a depletion region? Ang nangyayari, it flows very quickly across the depletion region because of the high electric field. There's going to be a high electric field here, and therefore your charge carriers will just sweep across the depletion region. So current can flow across a depletion region. That's how current flows in a diode. That's how diffusion current flows in a diode. But here, your channel actually is pinched off. And when that happens, increasing VDS will no longer increase my value of IDS. In other words, this pinching off will not become greater. It will just stay at this condition. And my IDS now will stay the same, regardless of the value of VDS. So here you show two modes of operation of your MOS transistor. We call this now your saturation mode, as opposed to here, which is your linear mode. And the value at which this happens, this is what we call VDS SAT, is just VGS minus VTH. VDS SAT is VGS minus VTH. Now you can see that there's some similarity with the BJT. In active mode, in a BJT, your collector current is not dependent on your collector to emitter voltage. It only depends on beta in active mode. Similar here, no, to a MOS transistor, you're going to find out later on that it's not going to be dependent on VDS. It's just going to depend on VGS. Your collector current, your drain to source current here will just now depend on VGS. It will not depend on VDS. Okay. Ang nakaka-confuse pag minsan, the flat area here in your MOS transistor we call saturation mode. In your BJT we call this active mode. And then in the BJT, the area to the left of active we call saturation, but here we call linear. So that's a little bit confusing. So the linear mode in a MOS transistor is similar to the saturation mode in a BJT. So these are your characteristic curves. Okay, so this is in increasing value of VGS. So in saturation, we mentioned that the value of your current, IDS, is not dependent on VDS. It will just depend on VGS. As you increase VGS, you increase the current in saturation mode. So this is for NMOS. For PMOS, as you could have guessed, we just reverse the subscripts. No? So this is now increasing VSG. Kanina increasing VGS, ngayon increasing VSG, where VSG has to be greater than or equal to the absolute value of your threshold voltage. Remember, in PMOS, your threshold voltage is negative. Okay. When it is less than that, it is cut off and you have no current. Okay. So these are the equations for your NMOS. Okay, so cut off is this. Okay, I sub D is equal to 0. ID is equal to I sub S, no? Because I sub G is equal to 0. Your gate current is equal to 0. Why is that so? Okay, that's because of the structure of your gate to substrate. It's a capacitor. At steady state, your capacitor current, if this is DC, is equal to 0. If it's AC, there's going to be a current. No? There's going to be a changing displacement current. But if it is DC, at steady state, your current is equal to 0. So I sub G is equal to 0, and therefore by virtue of KCL, whatever is entering here in the drain will leave at the source, no? Because this is equal to 0. So that's one difference between BJT and MOS. In a BJT, the base current affects the emitter current, no? But here the gate current will not have any effect on the source current. Okay, so this is for your NMOS. And for the PMOS, again, you just reverse the polarities. So remember, no? By convention, in the NMOS, we draw the drain on top, the source below, because we want to deal with positive values of voltages and positive values of currents. So in the PMOS, we draw the source on top and the drain below, so that we're again dealing with positive values of currents and positive values of voltages. So this becomes VSG, and VSD. No? So all the subscripts now interchange. So these are your models. This is your cutoff model. Okay, this is your, by the way, no, where did I get these equations? I did not explain where I got these equations. Hindi na natin i-derive to. We're no longer going to derive this. Okay, we're just going to ask you to remember it again. In when EEE 131 was first taught, we actually went through the derivation of these equations. Okay. But usually, yung mga estudyante, after reading through the derivations, first of all, they only understand half of it. And then because you don't go back to it anymore, they just forget all about it. That's the usual case. So here in this abbreviated course, we decided not to go through the derivation of these equations anymore. So take note that here in the saturation mode, hindi pumapasok dito yung VDS. The only thing that your ID is dependent on will be the value of VGS. No? Remember, VTH is a constant. So this is your only variable, no? VGS. But in linear mode, VDS will have an effect on Is of D. So in linear mode, no, your Is of D will be a function of both VGS and VDS. Okay. So again, going back to your models. Okay. So in saturation, your transistor is actually a voltage-controlled current source. So this current source from the drain to the source is controlled by the voltage VGS. And the relationship is a polynomial relationship. If you recall in the diode, not in the diode, in the BJT, okay, this is either, in the BJT, this is either a current-controlled current source when you use the relationship IC is equal to beta IB. So IB is your controlling variable. Or it is a voltage-controlled current source when you use the relationship IC is equal to IS e to the VBE over V sub T. VBE now becomes your controlling quantity. So here it's just a voltage-controlled current source, only depending on VGS. So this is for the Pmos. Again, this is now VSG, and this becomes absolute value of VTH. In linear, well, in linear, you can compute for ID, okay, from VDS and VGS. So kung alam mo yung VDS, alam mo yung VGS, you can compute for ID using this equation. But if we were to model the MOS in linear mode, the closest we can get to a model would be a resistor. Okay, that's by virtue of the characteristic curves. So we're here. Okay, so your current is increasing with voltage. That can be modeled by a resistor. Unfortunately, it is not a fixed resistor. In other words, the value of this RDS on varies depending on the value of VGS and VDS. So it's not a fixed resistor. It's a resistor that is dependent on two things, on VGS and VDS. If you will recall, sa EEE 123, we use this formula to approximate RDS on. 1 over K VGS minus VDH. Okay, you can do that dito, no? For small values of VDS, you can do that, because if you take a look at this curve, pag maliit yung value ng VDS, more or less this is a straight line. It is practically a straight line for small values of VDS. And in 1, 2, 3, most of the time ginagamit natin yung linear mode sa 1, 2, 3 in digital circuits. And in digital circuits, usually you're dealing with small values of VDS. That's why they allowed in 1, 2, 3 we allowed for you to use this approximation. But actually the value changes depending on where your operating point is, no? Because the value of RDS on is VDS over IDS, no? So if you're operating here, that's the reciprocal of the slope of the blue line, no? If you're operating here, no, let's say I'm operating here, okay, it's going to be the reciprocal of the slope now of this new line. So depending on where I'm operating, RDS on would be the reciprocal of this slope. Now, how do you compute for that? VDS over IDS, that's RDS on. This is your expression for IDS. Okay. So this VDS cancels out. May iwan na lang to. And I have to evaluate this at this particular value, no? At this particular value of VDS, which we call our operating point VDSQ. Okay. So if I do that, I'm going to come up with this expression. So this is a more accurate method of determining RDS on, no? So we use this usually in digital circuits, because in digital circuits, VDS is usually small, no? But this is the more accurate way of determining RDS on. Any questions? Any questions? Okay, so how do we analyze MOS transistor circuits? You're going to see that there's a parallel to analyzing Bjt circuits when you analyze MOS transistor circuits. The model that you use, so we describe 3 models: cutoff, linear, and saturation. The model that you use depends on the mode. Same thing with BJTs, no? It can be cutoff, it can be in saturation, or it can be in active mode. Okay. So the first thing that we have to determine is whether your gate to, well, I'm talking here about NMOS, no? I'm talking about sorry, no, in general pala to, no? First thing we have to determine is whether your gate to source voltage is greater than or equal to VTH. Because if the gate to source voltage is greater than or equal to VTH, no, sorry, this would reference NMOS, no? Because if this is PMOS, this should be VSG greater than or equal to the absolute value of VTH. I'm going to correct that later on. Okay, if VGS is greater than or equal to VTH, then there are 2 possibilities. You're either in the ohmic region or the linear region. No? If I did not mention that earlier, the linear region is also sometimes called the ohmic region. So either you're in the linear region or you're in saturation. If you don't know, you make an assumption. And the usual assumption that we make is we assume first that it is in saturation. If it is in saturation, these are your formulas for I sub D, depending on whether it's NMOS or PMOS. Then after computing for I sub D, we check whether the assumption is valid. And how do you do that? For NMOS, for it to be in saturation, VDS should be greater than or equal to VGS minus VTH. For PMOS, on the other hand, VSD should be greater than or equal to VSG minus the absolute value of VTH. Okay. If these conditions are correct, then tama na yung kinompute nating value ng I sub D dito, no? But if these conditions are wrong, then the transistor is in the linear mode, and therefore you have now to use this particular formulas. This is for your NMOS and your PMOS. Now, the difficulty with using these formulas is, okay, you have two unknowns here, no? Your unknowns here are VGS and, your unknowns here usually are VDS and I sub D. Because we don't know the value of VDS, no? Unknowns are VDS and I sub D. Okay. You have two unknowns, so usually you have to look for another equation, and that equation can be found usually using KVL. So you're going to have to solve for two equations in two unknowns, and most of the time it's going to be quadratic, and therefore you're going to have two roots, and then you have to choose which of the roots are correct. Okay, I think you've experienced doing that already in 1, 2, 3. So I'm not going to dwell on that too much. Take a look at the problems that you solved in 1, 2, 3, but also take a look at the problems that I published in module 4, part 5B, because there are exercises, particularly PMOS exercises, because you don't have that much experience with PMOS. There are PMOS exercises there, so take a look at them and try to familiarize yourself with solving this type of problems. That's all I have for now. Are there any questions? Any questions? Okay, if there are no, yes, please.
Sir, I have a question, sir, regarding yung sa VGS. So like, if VGS is less than VTH, yung channel is hindi siya may establish. So like,
that's right.
is that okay? So if it's greater than or equal to VTH, it establishes like the minimum, like minimum channel, like pinaka small na go through the channel.
Yeah. If VGS is actually yeah, VTH is the threshold voltage, it's the threshold voltage. We're not going to study the MOS transistor in that much detail, no? Because when VGS is a little bit smaller than VTH, meron tayong tinatawag na sub-threshold currents that flow, no? Kasi hindi naman biglang mawawala yung electron sa ilalim ng channel pag no? Pag let's say we're decreasing VGS, no? Let's say we're decreasing it so that it becomes slightly smaller than VTH. Your channel is not just going to disappear all of a sudden. There's still going to be carriers there, and those carriers can still contribute to current, but that current is not significant. That's why pag less than VTH, we just say the current is not significant. Pag greater than VTH, the current is significant, no? So medyo sinimplify din yung model nung MOS. Is that related to what you were asking?
Yes, sir.
Oh. Kasi baka iniisip nyo, and it seems yeah, it doesn't seem right na all of a sudden ibagsak mo lang yung VGS mo slightly below VTH, all of a sudden mawawala niyo yung current, no? It's not like that. There are that's in semiconductor physics they call that subthreshold currents, no? It's just that it's not significant. So when we solve problems in this particular course, we just consider it to be practically equal to 0.
Sir, so like once you reach like the VTH and then you go greater, so yung like channel it's gonna get bigger.
Yes, that's right.
Okay.
Think of it more like, kasi you might think of it bigger na talagang, well, yeah, the area gets bigger, but the concentration of electrons underneath the oxide also increases. So yung in effect yung resistivity natin bumababa or yung conductivity tumataas. Kasi yung value ng N, di ba, tumataas, and therefore if you compute for conductivity, tataas siya.
Okay, thank you, sir.
And then, do you understand pinch off? Bakit nagkakaroon ng pinch off? I hope that's clear, no? Any other questions? Sige, I'll leave, no? You can go now, but I'll leave when the last person leaves, so that if you still want to ask questions, I'm still here.
Thank you, sir.
Reminder, we're not going to meet anymore on Thursday, so I'm leaving it up to you to go through the material on op amps.
Thank you, sir.
You're welcome.
Thank you, sir.
Yes,
Thank you, sir.
You're welcome.